Hey, what's up, guys? Welcome back to Math 18A, College Algebra. Today I went outside for like 5 minutes, and now I'm having like allergies. I don't know how I'm gonna go back to living regular life after this. But anyway, one day at a time. And today's the day where we talk about logarithmic functions, which are highly related to exponential functions, which we studied earlier this week. So we're kind of just building on more functions that are not polynomials. So we're gonna keep studying that for now. So let's jump into today's lecture. Alright, so logarithmic functions. Like I was saying earlier, logarithmic functions are highly related to exponential functions, which we studied in the last section. So let's just go ahead and look at the definition of a logarithmic function. So for x greater than 0, a greater than 0, and a not equal to 1, we have that y equals log base a of x, if and only if x is equal to a to the power of y. And we also say that f of x equals log base a of x is the logarithmic function with base a. So the thing to keep in mind with logarithms is you can have this exponential form of an equation, and if we want to solve for the power, solve for the exponent on our base, that's why we would use logs. So let me do a quick example. We can say 16 is equal to 2 to the 4th, right? And this would be exponential form of this equation. But let's write that in logarithmic form. Well, all I have to do is compare this exponential version of the equation with my logarithmic version here. So the 16 is our x. So that's actually going to become the argument of my log function here. So the x goes here. My base is this a, so that's 2 in this case, right? So that becomes the base of my logarithm as well. So log base 2 of 16. And then the y is my power, the exponent on the base. So here, that's 4. And so the way to read this is sort of looking at this 2 to the what power is 16. So just keep in mind that logarithms help us solve for exponents. That's their main purpose. So here are some examples of some common problems you might run into when studying logarithms. So let's go ahead and take a look at the first one. Log base 9 of 81 equals what? And so again, the thing to keep in mind is logs help us solve for the exponent, right? So when you see this, you want to be thinking 9 to the what power is going to give me 81. And whatever is in this circle here, I'll make it green as well, is your answer. Because logs solve for the power, right? So 9 to the what equals 81. Well, 9 squared is 81, right? So then my answer is 2. 9 to the second power is 81. So that means that log base 9 of 81 equals 2. Okay, let's take a look at the second one. Might be a little bit more tricky to figure out exactly what we want to do here, but again, we start with the same process. 7 to the what power is going to give me 1 over 49. And so here, you're thinking, it's kind of strange that we have a whole number, 7, and then we end up with a fraction, right? But remember that negative exponents give us that 1 over something. And then you're just thinking, 7 to the what power do I need here? Well, 7 squared again is 49, right? So I'm looking for 1 over 7 squared, which is 7 to the negative 2. So in this case, our answer is going to be negative 2, meaning that log base 7 of 1 over 49 is negative 2. Alright, and another thing that I want to point out when solving logarithm problems is if you have a problem that is log base 10, then this is solvable with your calculator. Your calculator should have a log button. And this log button is always log base 10. At least on like almost every single calculator that I've seen. So you can plug this one into your calculator and it should give you the right answer. But we can still take a look at it anyway. Let's think of 10 to what power gives me 1 over 100. And so that's almost the same problem as this 7 to the what gives us 1 over 49, right? Because we're still looking at negative exponents. And then we notice that 100 is 10 squared. So this one would also be negative 2. But this one is verifiable with your calculator. So make sure you give that a try at some point. Next, I'd like to cover some of the properties of logarithms. And these are just a few of them. The next section, 4.4, is actually completely dedicated to covering properties of logs. But these are the first 4 that we'll want to take a look at for this section. So first, log base a of 1 equals 0. And if you think about it in exponent form, you can see a to the 0 power equals 1. So, and that's for any a. You can take any number to the 0th power and it should be 1. Second, we have log base a of a equals 1. And again, you can think about it in exponent form. A to the 1st equals a, because taking to the 1st power we're not multiplying anything there. For the third one, log base a of a to the x equals x. We can also think about that in exponential form. A to the log base a of x equals x. And so the thing to notice about these ones is that log base a and a to the x, those are inverse functions. Your exponential functions and your logarithmic functions are inverses of each other, as long as you keep the same base. So we can see that this log sort of undoes our exponent here, and that's why we end up with just x. And then finally, number 4, if log base a of x equals log base a of y, then x equals y. And that property is called the one-to-one property of logarithmic functions. So let's now take a look at what the graphs of logarithmic functions look like. And to do that, we're going to use our exponential graphs that we saw in the last section, and one of the properties of inverse functions. So let's take a look at this example. Graph f of x equals log base 2 of x. And so we're going to use the corresponding exponential function. We'll call it g of x equals 2 to the x. So let's first actually graph this g of x equals 2 to the x. So I'll make a table of values here. X, g of x. And we'll just go from negative 2, negative 1, 0, 1, 2. Alright, so plugging back in to this g of x, we'll plug in negative 2 for x, so 2 to the negative 2 equals 1/4, because it's 1 over 2 squared, right? That's what negative exponents do. And then for negative 1, I'll have 2 to the negative 1, which is 1/2. For 0, I will get 2 to the 0, which is 1. For 1, I'll have 2 to the 1st, just 2. And for 2, I will have 2 squared, which is 4. Okay, so let's go ahead and plot these values. And let's go negative 1, negative 2, 1, 2, 1, 2, 3, and then 4 will be up here-ish. 4. Okay, so negative 2 comma 1/4, so it's going to be pretty close to the axis here. -1 comma 1/2, that'll be right here. 0 comma 1 will be right here. 1 comma 2, that'll be here. 2 comma 4, that'll be way up here. Ish. And I'll trace those in green. So I have something like that. I didn't quite pass through this 4, but it's going to look something like this for our exponential function. And so the next thing to do is remember that log base 2 of x and 2 to the x are actually inverses of each other. And so if I have a table of values for one of my functions, and I want to find the table of values for the inverse function, all I have to do is swap the x and g of x values, and that'll give me a table of values for my f of x here, this log base 2 of x. So we're first going to look at our g of x values, and those will become my x values here. So 1/4, 1/2, 0, or no, not 0, sorry, 1, 2, and 4. And then you fill in their corresponding x values, which are now my f of x values, so -2, -1, 0, 1, and 2. So let's go ahead and plot those on our graph here. We have 1/4 comma -2. I need to make some markers for -1, -2. So 1/4 is going to be around here, pretty close to the y-axis this time, and -2 will be down here. 1/2 comma -1, so 1/2 here, and then -1. 1 comma 0, so 1 here, 0. 2 comma 1. And then way out here, 4 comma 2, so it should be somewhere out here. And let's go through those points. So this blue curve here, this is our log base 2 of x graph. And the green one is the 2 to the x. And so hopefully you'll remember with inverse functions, the graphs are supposed to be symmetric over the line y equals x, which is this line through here. And so if I'd scaled it correctly, you can see that if I reflected over this line, you should get exactly this other function, or inverse function, this log base 2 of x. So yeah, that's how we're going to be graphing these log functions. Alright, so now let's take a look at some transformations of graphs of logarithmic functions. So just like our exponential functions that we looked at last section, we can do shifts, we can also do reflections, we can also do, stretches, vertical and horizontal stretches. I'll do a quick example of those as well. But first let's just understand shifts. So just like with exponential functions, we can shift horizontally by taking our graph log base a, but instead of just x, we'll have x minus c. And that shifts c units, either right or left, depending on the sign of c. If it's positive, it'll shift to the right. Is to the right, and negative c goes to the left. And then similarly, we can shift vertically. And we do that by adding or subtracting some constant. Call it d here. So shift D units here too. It'll be up if it's positive D. And likewise, if it's negative D, we'll shift down. We can also reflect our graphs of logarithmic functions over the y-axis, and that looks like log base a of negative x, or over the x-axis would be negative log base a of x. Finally, another transformation that we can do to our logarithmic graphs are stretches, so vertical and horizontal stretches. I didn't mention these when we did exponential functions, but figure I'll mention them now just because it's been a little while since we've done them. And to do a vertical stretch, all you have to do is throw a constant in front of your graph where this b is greater than 1. So consider, for example, 2 log base 10 of x, rather than just log base 10 of x. Well, all that does to my graph is makes it grow a little bit quicker. You can imagine if you made a sign or a table of values, every f of x value that you end up with just gets doubled because of this multiplication by 2. So if this is the graph of, oops, not like that. If this is the graph of just log base 10 of x, then if I'm scaling it by 2, doing a vertical stretch, it'll just grow more quickly. Alright, and so for horizontal stretches, very similar. You'll have some constant on the outside, b times log base a of x, but here we'll have b is less than 1, but we'll take it positive still. Because remember, if we make it negative, that's a reflection instead. So we'll take positive values, but less than 1. So again, I'll draw the graph of log base 10 of x, something like that. And so let's say, here, let me write the example out. Log base 10 of x, but let's say we transform it to 1/2 log base 10 of x. Well, that doesn't quite grow as quickly as log base 10 of x, so it's going to grow slower than our log base 10 of x, so something like that. And then the last real concept that I want to introduce in this section is the natural logarithmic function. So you'll remember we had our exponential function where we had the base e, which was Euler's number. Well, of course we have a corresponding logarithmic function. So the function defined by f of x equals log base e of x equals natural log of x, and this is how we denote that. It's an ln. I do like a script L and then an n. Doesn't look as nice there, but that's how it's denoted. The natural log of x is how you say that. We'll quickly go through some of the properties of natural logarithms. They're quite similar to the properties of regular logarithms. Just keep in mind that this natural log is base e. So first we have natural log of 1 equals 0. Again, because e to the 0 equals 1, like every other base. We also have that natural log of e equals 1, because e to the first equals e. We have natural log of e to the x equals x, and likewise e to the natural log x equals x, so you can think about this natural log as the sort of inverse function of e to the x, right? They undo each other, essentially.
And finally, if natural log of x equals natural log of y, then x equals y. And again, that is the one-to-one property of logarithmic functions. I'll just say of logs here. Alright, let's now go through some examples of how we can do natural log calculations. So we'll look at natural log of e to the 7th. And so here we want to use that property 3. Natural log of e to the x equals x, right? Because we have something of that form. We have natural log of e to the 7th. So just sort of plugging in, we saw that natural log e to the x equals x. So natural log of e to the 7 equals 7. This natural log undoes the e, and we're just left with the power that we had on our e here. Alright, let's go ahead and look at the second one here. 5 natural log of 1. So let's go back and take a look. Natural log of 1, using property 1 here, is 0, right? So that means that this part, natural log of 1, evaluates to 0. And then we're left with 5 times 0, which is just 0 still. Let's look at the last one now. We have 3/4 times natural log of e. So once again, let's go back and look at our properties. The property 2 looks like something we'll want. Natural log of e equals 1, right? So this part, the natural log of e, evaluates to 1. So we have 3/4 times 1, which is just 3/4. So it's really just a matter of knowing how to simplify these expressions. So these properties will come in handy a lot for that. So just make sure you can use these, apply them to whatever problems you might encounter. Alright, let's go ahead and do a word problem example. Biologists have found that an alligator's length L in inches can be approximated by the model L equals 27.1 times ln W, natural log W, minus 32.8, where W is the weight in pounds of the alligator. Find the lengths of the alligators with weights W equal to 150, 225, 380, 450, and 625 pounds. And we want to round to the nearest tenth here. So, seeing this equation, you should definitely be thinking, this is a calculated problem. So I want to find the corresponding lengths of alligators with these widths that we've listed here. So all we have to do is plug in these different values of L into our calculator. And so the way that I would do that is start with the natural log, the ln. There should be an ln button on your calculator. Let's start with the 150, and we'll just take ln of 150. Find that first. Then we want to multiply by the 27.1. And lastly, we subtract the 32.8. So you always want to make sure you do things in the correct order, right? So first you plug in, resolve this part, then you multiply, finally you subtract. So when I get that, when I solve that equation, I end up with 102 points. So I get 0.988. But let me show you this real quick. So I want to round to the nearest tenth, right? And the nearest tenth is this spot. So if I'm looking at the next digit, this 8, I'm going to want to round up. But I don't have anywhere to round up. I'm already at 9, the largest that this digit could possibly be. So this is actually going to round. I'll write the rounded answers down here. This is actually going to become 103. Oops. 103.0. It's like carrying a 1. Rounding this 9 up to a 10 and then putting it into the next place over, the 1's place. And so the length was in inches, I believe, so we'll put inches. So that's what we get from the first W here. So let's go ahead and try the second W. Again, we'll take ln first, ln of 225 now. Then we take that answer and multiply it by 27.1. And then we subtract the 32.8. And so then I end up with 113.9 7. And once again, we have the same sort of problem here. We want to round to the nearest tenth, this position. We look at the next number, and it's a 7, so that means we round up once again. So that means that, again, I have to take this up to 114.0. Alright? Let's go for the third weight. So we want to take natural log ln of 380, multiply that answer by 27.1, subtract the 32.8, and I end up here with 128.17. Again, we'll be rounding to the nearest tenth, so we look at the first number after the decimal, and it's a 1. Looking at the next digit over, it's a 7, greater than 5, so that means I'm rounding up, right? So I'm going to end up with 128.2 inches here. Okay, let's take our fourth W, a natural log of 450. Take our answer, multiply it by 27.1, subtract 32.8, and I end up with 132.76. Looks like all of these were rounding up. So here we have rounding to the nearest tenth, so the 7's place. We look to the next digit, it's a 6 greater than 5, so that means we'll be rounding up once again. So then we end up with 132.8 inches here. Finally, our last W value, 625. We'll plug it in, natural log of 625. Take that answer, 27 times 27.1. Subtract the 32.8. And remember, it's best to do our calculations first and then round at the very last step to get the most accuracy. So that's what we've been doing here. So we end up with 141.66. Rounding to this position, looking at the next digit, it's again a 6 greater than 5, so that means that we will be rounding up once again. Alright, and that's all that I needed to cover today. Next time we'll be going more in depth on logarithms again. The textbook splits up the logarithm section into 2 different sections, so I think that's why today was a shorter lecture. But yeah, see you next time for more logarithms.